in the previous session, we said that we determined what happens after we increase the magnetic field from 0 to a small value. And so we see that here there will be an increase of the velocity by a small b here. Now this means that the magnetic moment will increase. So if you look back at the image here, so the b will increase, and however, what we assume is the b is along the positive z direction. This means that the total change of m will be in the opposite direction of the magnetic field b. So now you can sort of see that what happens, say I change the direction of m. So remember that for a material, the direction of the m is random, right? So it can be an arbitrary direction, and for some of the orbitals, it can even be parallel to the z. But for that case, then the electron is rotating on the opposite direction, right? So now for the if you add a magnetic field, the centripetal force will pointing outwards, so it will reducing the centripetal force, and in this case, the total velocity will be reduced. So the change of this m will still be in the negative z direction. So you can sort of see that somehow for any direction of this magnetic dipole moment, the change of this m is always opposite of the direction of the magnetic field b. So that's why we call this the diamagnetism. So here, for different orbitals of the electrons, the change of this magnetic moment m is finite, and is always anti-parallel to the b, or is always opposite to the b direction. And even though that the average of this m is always 0, so hopefully now you can actually know at least qualitatively the mechanism behind the diamagnetic material. So in reality, to quantitatively explain the phenomena, it's actually a quantum phenomena, because this is electron clouds, right? So you have to use quantum mechanics to for a deep understanding. But here, using classical electromagnetic theory, we already know there must be a diamagnetic material, and sort of understand how the reasoning behind this diamagnetic materials. So I want to also note that our discussion here does not only apply to materials with completely filled electron orbitals. It also applies to every materials. So even paramagnetic materials. So except that this is a small effect comparing to the paramagnetism. So the magnetic field will align this spin up electrons, and the magnetic moment will align with the magnetic field much easier than this diamagnetic mechanism kicks in. So the effect is dominated by the paramagnetism effects of the spin of the electron. and this orbital motion are small corrections to that effect. So for paramagnetism, this effect is negligible, and only for the case where there are no total magnetic dipole moment produced by the spin of the electron, does this diamagnetic effect becomes important. So now we can try to summarize what we have. So just like what we did in the electrostatic case, we can always also define the magnetic dipole moment per unit volume as this m vector, the magnetization, and this is similar to the p vector here. So in principle, because the materials either are paramagnetic or it's diamagnetic, so somehow there must be some interaction between most of the materials with the magnetic field, right? But in reality, if you move a piece of wood close to a magnet, you don't see anything happening, right? So that's because this effect is actually extremely small effects. So only for a ferromagnetic case, so if you put two ferromagnetic ions together, then they will either repel or attract. That's because their effect is like 10 to the order of 10 to the 5, much stronger than the effects of this paramagnetic or diamagnetic case. So there is actually a interesting or funny experiment done by Andrew Game that they actually, in principle, a diamagnetic material can interact with the magnetic field. So actually a live frog has been levitated by using the magnetic field alone. And to
like human.
what?
Levitated like human.
That will be extremely hard, right? And also it's the magnetic field is also too huge. Like a huge magnetic field actually is not safe. So when you go to NMR, and you actually have to.
How about the frog? Maybe the frog feel unsafe as well. Did they ever think about the frog itself?
So he actually won an IG Nobel Prize for that.
Maybe the frog doesn't even like to be levitated.
Levitated astronaut, that would be ethical.
It's actually interesting that 10 years later he actually won the actual Nobel Prize, based on the research on graphene.
Doing inhuman experiment win him a Nobel Prize. Okay.
So he is the only person that won the IG Nobel Prize and the true Nobel Prize. Just a fun fact. Okay, so now let's try to go to the next section. So previously in the electric fields with materials, we also discussed what kind of fields will polarized material produce, right? So if you still remember the exams, the question 2 and 3, I tried to ask you to derive how to calculate the induced surface current and the induced volume current of a polarized object. So here we are also interested in to see how to calculate the field of a magnetized object. So here we don't know how this object becomes magnetized. So it can be a ferromagnetic, or it can be para or diamagnetic. But there are already um, there is already a magnetization vector, so the capital P, capital M, that's in here in this object, and this means that for each small volume, the tau prime, that's the source, we have a finite magnetic dipole moment M. And now, in principle, if we want to calculate the vector potential, we can simply use what we have just derived in the last lecture, use the equation of the multiple expansion. So here I'm simply copying the equation of the leading order multiple expansion here, because for magnetic field, the leading order is dipole order, so the order here, separation vector, is power of 2. Now, if you want to get the entire magnetized object vector field, you simply integrate this expression over the objects. So here we want to keep in mind that the integration is with respect to the prime coordinate, and here the m vector is also with respect to the prime coordinate, because that is the source, and there is a separation vector here, curly r, and that is defined always as a vector between r and r prime. So here from this this one actually relates the source and the observation point. So what we get in the end is the total vector potential at arbitrary point. Now, in principle, that gives you everything, right? So remember that in the exams, we use integration by parts to rearrange the terms here, and somehow generate two terms. One term is a surface term, another is the volume term. So here we do the same thing. And by the way, if you want to look at the derivation, you can also go back to check the solution to the midterm. So I've already posted the solution to midterm online at the PDF section. So you know how to you should know how to look up this. So here to calculate or to simplify the expression over here, we can actually identify the separation vector hat over separation vector square. This term, this is simply the electric field expression for a point charge, right? So then that the corresponding scalar potential is 1 over the separation vector. So now we can replace the expression over here by this del prime 1 over separation vector. So I simply copy it down here. Now this expression we can use the integration by parts, because you see that somehow the del prime operator is only applied to one term. So we can pull this out and apply into the two terms combined, and this should be able to transfer to a surface term. And we can also apply the del prime to the m vector here and pull this out. So So the integration by parts. So you can actually look up the formula here on the front page of Griffiths, and if you so for the second term here, if you look up your homework 1, the question 1b, you can actually see that this term, there is the similar Stokes theorem for for expression like this. So you can finally express the del cross v in terms of minus v cross a. So it's a generalization of the Stokes theorem. Now, if we rewrite the terms here, in the end, we get one term on the left here, simply copy down, and the second term, and by rewriting the term here into a surface term. So to clarify, this is a volume and this is a surface. So now, if we compare what we have done in the electrostatic case, we immediately see that here the terms in the parentheses should be a term of source current. So this del cross M we can actually replace by this J volume current, because this is exactly what a volume current produces the vector potential. And so the second term, we can actually also identify that this is actually a form of a surface current. And by now we can simply rewrite the right hand side by M cross N hat dA. And so here, if we compare the expression here with this with the expression of a vector potential for a surface current, then we see that here this K cross N has to be a surface current K, and so this gives us our final expression for this vector potential. So for a magnetized object, we can separate the contribution to the vector potential by two terms. So one is a term produced by a volume current, another is a potential caused by the surface current. So now if you compare what you learned in the electrostatic case, the surface charge is P dot N, and the bound volume charge is minus del dot P. So these two actually share a lot of similarities. The electrostatic case and the electromagnetic case are really similar to each other. So here, let's try to find an example. Here's the example here is to find the magnetic field of a uniformly magnetized sphere. So remember that we also did a similar calculation on a polarized sphere, right? So
We thought you brought a polarized sphere.
what?
We thought you brought a polarized sphere when you go back to your bag.
Oh, okay.
I'll bring one next time.
Yes, definitely. Yeah, I should actually bring more like toy models, and
Yes,
that will be
please.
fun. But this is the first time I'm teaching the course. Like, I don't have too much time to prepare for this kind of this kind of toys. And I think that will be fun for the teaching. Like, probably when you have already graduated. Okay, so now this problem is extremely similar to the electrostatic case. So I believe that should be in lecture 9. So you can go back to look for the similar problems. So for our case, what we need to do is simply to calculate the bound and the bound volume and the surface current, right? So let me go back. So we simply use the two equations over here. So the volume current is del cross M. So here the del cross M is easy to calculate because here I specified a uniformly magnetized sphere. So the M itself is homogeneous or is uniform within the sphere. So because that means that M is a constant within the sphere, so that the curl of that constant should be 0. So if you want, you can specify it's a vector, but it's a constant 0 vector anyway. So it doesn't contribute to any volume current. Now, to get the surface current, we have to use the M cross N term. So here the bound surface current must be written as M cross the N hat, where the N is the direction of the surface. So here the for uniform sphere, the surface direction N hat is along the radial direction, so along the R hat. So that gives M cross R hat. So here M is along the Z axis. So here it's the magnitude of M times C hat cross R. And so the angle between the Z and R is theta. So if you calculate the amplitude, that should be M sine theta. And now let's determine the direction of this surface current. So here this direction is Z cross R, right? So it must be in the either pointing into the screen or out of the screen. So if you use the right hand rule, so go from the Z to the R direction, and then that should be give you a direction that's pointing into the screen. So say for the point over here, the direction must be into the screen. So that is along the direction of the phi direction, right? So here the KB must be along the phi direction. Now here comes actually the interesting part. So we've calculated the surface current of this uniformly magnetized sphere, and it produced a surface current along the azimuthal direction. So I don't know if you still remember in the lecture 14 or the lecture before today on last Thursday, we actually calculated what happens if you rotate a charged sphere. So a charged sphere gives you a current along the azimuthal direction, right? So you see that this problem actually can be mapped to a problem of a charged sphere. So the exact mapping, let me see. Okay, it should be here. So for a charged sphere with moving with velocity v, then the current surface current is k equals sigma v, and now if you express the v as omega r times sine theta, you can actually get a 1-to-1 corresponding by replacing the sigma omega r to this polarization vector m. So now everything we have calculated for a surface current problem or a problem with rotating charged spherical shell can actually directly apply to here. So in that problem, we actually calculated the B field. So the B field inside the sphere, we write down this as mu naught sigma r and omega, and here then we simply replace this sigma r omega by this m, and that directly gives us the B field inside. So the B field inside is actually proportional to the magnetization vector m. So here in the inside, it's also a homogeneous magnetic field. And outside the B field, we can use our calculation of the vector potential for that problem. And if you compare the field outside, it's identical to a field produced by a perfect dipole. And the perfect dipole moment is simply the integration of the magnetization vector and the volume over the entire volume, and the volume is 4/3 pi r cubed. And now, if you compare what you have just calculated in lecture 9, if you still remember, for a uniformly polarized sphere, you also get E field that is proportional to the polarization vector inside, and the outside is also similar to a field of perfect electric dipole. So the factor here inside is different, but outside the field is actually identical.
Can I ask why is it 2/3 Why is it?
What do you mean, like?
The B field of the rotating.
Oh, wait, there's last class.
Yes.
Yeah. Okay, so this equation is because from the last lecture we calculate the B field of a rotating charged sphere, and that's the equation here, and we simply copied the equation over here by identifying the correspondence. Okay, so we will actually talk about this more in hopefully next Monday. So now let's take a look at another example. So here, what we calculated before was a uniformly polarized sphere. Now let's do a same thing to a different object. So now I want to calculate the uniformly polarized cylinder. So this might give you more 3D. So for this uniformly polarized cylinder, let me see. So assuming that here the magnetization vector is parallel to the axis of the cylinder, and now we try to get the magnetic field both inside and outside the cylinder. So we do the exact same thing. So we first calculate the bound volume current. So it's the J bound, which is del cross M. I guess that's correct. Okay, yeah. So the del cross M should be exactly 0, just as what we argued before, because it's a uniform M, and so the M doesn't depend on the coordinate when it's inside the object. So what we have left over is to calculate the bound surface current. So the bound surface current is M cross N, right? So it's the M direction cross the surface direction. Now let me see. So here we want to calculate. So because this surface, we are considering an infinitely long cylinder, so the surface on two sides doesn't matter that much. But if you insist on cutting this cylinder, if you go a long enough cylinder, then the M cross N should still be exactly 0, right? So let me see. Because N is parallel to the direction, or anti-parallel to the direction of the polarization vector M. So at the two sides there is no contribution. So only on this on the side of the cylinder there are contribution to the bound current. So let's try to draw a point. So suppose there is a point on the surface on the side, and now the M is along the Z direction. So Z direction, and the N hat direction is the radial direction. So what you can have is what is normal to the Z and the R hat direction is the azimuthal direction or the angular direction in this cylindrical coordinate. So it has to be phi direction. Let's try to see what's the exact is that. I guess that also depends on how you define the direction. So it could be either a plus sign or minus sign along the phi direction, but you can use the right hand rule to determine the exact direction. So now you see that now you see that actually the surface current is along the azimuthal direction, means it's actually similar to a solenoid, and we just calculated the magnetic field with of a solenoid in previous lectures. I guess that might be 2 lectures before. So for a magnetic field of a perfect solenoid, if you still remember the conclusions, then the magnetic outside is exactly 0, and for the magnetic field inside that cylinder, the magnetic field if I copy the solution from the previous lectures, is mu naught I, which is the current of the solenoid, and N is the number of wrapping per unit length, so the wrapping density, and Z is the direction along the axis. And now you can simply identify that the I times N. So remember that N is the wrapping per length. So the I over the length give you a current of a surface current, right? So the IN can be combined into the K. And we also have the K. Here, this K is proportional to the N, right? So now the B inside should be actually can be expressed as mu naught times the magnetization vector M. So in the end, we get an extremely simple answer. So outside is 0, and inside simply mu naught times magnetization vector M. Okay, so we finished the lecture 5 minutes early today. So this is the first lecture on magnetization in materials. We will have 2 additional lectures. Remember that the homework for the previous chapter for magnetization in vacuum is due on Thursday. And on Thursday, I will also give out new homeworks on this chapter. But this chapter is a bit short, so you will expect much shorter homeworks for this chapter. Okay.